Okay, I think you guys probably, I hope in the videos online that it gave you kind of a little bit of a background on why they call it the T-test. It was originally invented by a statistician for a brewery that they would change formulations. You know, yeah, obviously certain things in beer that you're interested in. Probably one of the most important is the amount of alcohol that you produce, and you may change the amount of alcohol depending on what kind of malt that you use. It may have to do with the temperature that you ferment at. It may have to do with the type of yeast you use, and so on and so forth. There's a lot of variables. That's why there's 8,000 microbreweries now, and every one of them has got 27 different kinds of beer. It's not like 1960 where you go in and you got Bud and you got Bud Light. That's it. In fact, I don't think they had Bud Light then. But I mean now there's many specialty breweries and stuff, and they taste different. There's different quantities of alcohol in them and stuff because there's many different factors that influence what the product comes out looking like. So the problem with that is that as a brewer, he was dealing with relatively small samples. They'd make small batches. So they would make this formulation up, they'd make a batch of it, right? And then maybe make another batch and another batch. So you only had 3 or 4 times that they made these small batches. So as far as the alcohol was concerned, he would have to find the average from his 4 samples, the average, what he thinks that technique or that blend would produce based on those 4 samples. And then if they change something, he might make 3 or 4 more batches to see how they look to find the average for them. Now he had to make a judgment. Is the average, if the difference in the average for batch A versus batch B, type A versus type B, is that difference, just due to chance that it happened that the few times that I brewed it, this one came out a little higher, on those days? Or is it really due to the fact that the formulation gives you a different alcohol content? So there was plenty of information about dealing with it. There's plenty of ways for these guys to reliably guess if they had a lot of samples. I mean, many batches to reliably say whether or not formulation A was better than formulation B. But when they were dealing in small batches, it was much more difficult. So he developed a technique for determining whether or not you could reliably say that with using small samples that type A, the mean for type A or formulation A is different from the mean for formulation B. In his case, might have been the alcohol content. In our case, it's any numerical variable, because you can apply this to any numerical variable where the population has a roughly normal distribution. Okay, so that's one of our assumptions, right? That we have a population with a roughly normal distribution. Well, we talked about the central limit theorem, and we said, oh, well, Tony, didn't you say central limit theorem? That you didn't have to worry about that when you took repeated samples. That even if the distribution was not normal, the repeated samples would become normal. Well, that's true up to a point. If the sample sizes are small, right? If each of your sample sizes is 3 or 5 or 7, it'll start to get normal it'll be more normal than the population distribution, the distribution of the sample means, but it's not really until you start to get a very large sample that it'll really work pretty much all the time. So when we talk about a t-test, very frequently we're talking about a small sample size. 25 people, 10 people, 5 people, and so on and so forth. So it's not quite as reliable. So in that case, we have to make up for that uncertainty. And that's where the t-test comes in. And that's why when we have a very large sample size, we just use, when we want to be 95% certain about something, we just use 1.96 because that's the normal distribution. That's a Z table for the normal distribution. When we have a small sample size, 20, 25, 10, then we have to make up for the fact that we're less certain about the variability that we're dealing with here. We don't know the population standard deviation. We're less certain about the variability. So our spread, the distance apart, the two means have to be in order for us to say that there's 95% certainty that they're really different means. The distance that they have to be apart is now further apart. In other words, if I have a big sample, and if I have a big sample, they can be closer together because I'm more certain about the variability. If I have small samples, they have to be further apart because I don't know what the spread really is. So if I get 100 here and 110 here, I don't know really, how reliably I can know that, but I need to know what the variability is as well. So in order to make up for that level of uncertainty, we use a t-distribution. T-distribution is just like normal distribution, except it tends to flare out more, right? So it's wider. So the t-distribution has different values. The z-distribution, if you know the population mean, population standard deviation, the z-distribution describes any normal distribution. And there's one table that goes along with it. And we know that 95% confidence is represented by 1.96 standard deviations above and below. On the other hand, now that we're working with smaller samples, we have to be further out. So the number of standard deviations away that we have to be, as the sample size gets smaller, we have to be further apart in terms of number of standard deviations. With samples, we call that standard error, as a matter of fact. Okay, so in other words, if we have a giant sample size of 1,000, right? Well, then 1.96 is basically pretty close to what you would use. Might be 1.9601 or something like that. If we have a sample size of 100, it might be 1.98 standard errors apart instead of 1.96. Got to be a little bit further apart. For a sample size of 20, it might be 2.3 standard deviations, standard errors apart, right? So depending on the sample size, that's going to determine what that number is in your confidence interval, and also determine when you use the t-test whether or not you accept or reject the null hypothesis. So a small sample size means a bigger value for t critical and t that you use in your calculation of the confidence interval. Okay, so I'm going to open this up and we're going to quickly write down a few steps here. Okay, so number one, actually I'm going to open up a file here, if I can find it. Data sets. There we go. Okay, tell you what. Oh, I don't think I put this on Blackboard. I'm going to put this up on Blackboard right now for you guys that are at home, or you guys that are on your computers that want to use it, that want to do this with me. Yes.
Quick question.
Yep.
With the margin of error, you said that we would just, if it's a large sample and or the
Population standard deviation.
we would just use 1.96 times standard error.
That's correct.
If those are not present and we are known, then we would use the t-score times standard error.
Correct. Yes.
And that would be the margin.
That would be for a small sample or when we don't know the population standard deviation. In real life, you're almost never going to know the population standard deviation. So I'm going to put this in the most recent weekly materials. I have a data set here. Let's see. I'm sorry. What's that? Oh, I'm sorry. Oh, here? I don't know. Maybe it's possible. Yeah, I'll have to take a look. Okay. Actually, I'm just going to post it. I'm going to put it right there. Make it easy to find. Let me go back.
What is that you have biostat for, you're teaching biostats in Hunter College?
Yes.
Is that undergrad or grad?
That's graduate also, yeah. Mostly nutrition students and nursing students.
It's equivalent to this school, right? To the SPSS program?
Yeah, it's roughly equivalent, yes. This is like 600 and 600. There's also a more kind of intense version of this at 611 and pH 751. You guys have to go, eh? Okay, well, you guys will be able to, I'll get this posted. Practice data. Okay, branch my computer. And where did it go now? There it is.
They have to take it in the Hunter and transfer.
We're getting it in the summer. Are you going to be around in the summer?
They're telling me that I'm taking too many classes in the summer.
Oh, no.
It's not ideal.
Yeah. Nice thing about the summer is you're done in 8 weeks.
How intense is it? Is it like?
It is, yeah, but you meet twice a week. So,
you meet?
Twice, yeah, yeah, twice a week. Oh, yeah, that version. There may also be an online version. They haven't talked to me about that yet.
There's an online version.
Yeah, yeah.
I didn't sign up for it yet because it wasn't the game. So I was like, I'm not sure.
Okay, so practice data. You can take it with someone else. I mean, they're good teachers also, you know. Okay, so at any rate, let me open this file up and we'll take a look at the data in here. Hopefully this will be the file that I'm interested in. Okay. I double clicked it so it opened it up twice. Let's open it up again. There we go. Okay. So I don't actually, this is a survey. This is some survey data. And I'm going to just quickly show you the variable view. And in this, we have gender, we have sex of the individual, that's individual subject, the age of that subject. It has, for instance, whether or not they're a smoker. And if I click in here under the values, it tells me that 1 represents yes, they're a smoker, and 2 represents no, they're not a smoker. Okay, and let's see, if I scroll down further, I see that there's these various things called TP, so on and so forth, this, that, and the other thing. And what that really stands for is self-perceived, for instance, this one, total self-perceived, total perceived stress, total perceived stress after. Okay, I'm going to change that to after. I didn't edit that. I edited the name, but not the label. Okay, total perceived stress after, total self-esteem. They would rate this on a scale, say 1 to 100 or something like that. So that is a scalar or a numerical variable. So as I'm looking at this, I'm seeing gender is a nominal variable, male or female. Age is a numerical variable. Marital status is a categorical variable, but marital status has more than 2 values. A single, steady relationship, remarried, so on and so forth. Whether or not a person has a child, that's a yes or a no. That's also a yes or no variable. Okay, so we have a lot of nominal variables that have 2 groups. Has a child, don't have a child, male, female, so on and so forth, right? And there are a lot of other, those are nominal variables. There are other numerical variables that I can use that might be of some interest for me to compare them. Okay, so one of the things I might be interested in looking at is perhaps the average age of people in this survey with regard to their gender. Okay, so what would we be looking at here? So these are random samples from a population, for argument's sake. And in these random samples from a population, we surveyed them and we asked them for their gender and their age. Okay, nominal and numerical. Okay, so let's say I'm interested in knowing whether the females in this population have the same age, yeah, same average age or a different average age than the males do. Okay, now keep in mind when we're talking about this, I have a sample here. It's 400 people in this sample. I don't care about what the mean is for the females in the sample and the males in the sample because it's just a random sample. I'm interested in what the average age of the population is. Unfortunately, I'll never know what the mean age for females and the mean age for males is. Because unless I take a census of the entire population, I'll never have that information. The closest that I have is I have the average for the females and the average for the males. And I need to make that work from here. I also don't know what the variabilities of these 2 groups are. The variability of the females, that would be sigma for the females. Variability of males, that would be sigma for the males. I don't know that either. All I know, all I can get from this is the variability of the samples themselves. In other words, standard deviation for the females and standard deviation for the males. I'm lucky in that the mean of the population is approximated by the mean of the sample. Bigger the sample is, the more reliable that is. Same thing with the standard deviation. The standard deviation of the sample approximates the standard deviation of the mean. Bigger the sample size is, the better, the more reliable is your estimate of the population, the standard deviation of the population. Okay, so let's say I want to compare these two means. Okay, so group A, right? I want to compare the mean for female versus male. Okay, so the first thing I need to do is I need to establish a null hypothesis, a starting point. My starting point is always an equality, right? So my starting point is the assumption that the mean age for females in this population, notice I used mu, is equal to the mean age for males in this population. Well, now that I have established that, what I'm really trying to show, or what I really think is maybe the age is different. Maybe people in this population, maybe there's more older women in this population. I think that the females, that this is not true, is what I'm trying to demonstrate. We start with the null hypothesis, but even though we want to actually prove that the age is different. So let's say we're looking for the alternative hypothesis, that the mean of the female's ages is equal to the mean of the male's ages. Again, the population is not equal to the mean of the male ages. That's my alternative hypothesis. Okay, so now at this point, I've established my null hypothesis, my alternative hypothesis. At this point, I have to establish what level of certainty do I want to accept here. In other words, what level of, do I want to be 95% certain? Do I want to be 99% certain? In this instance, we're going to describe that level of certainty by the level of error that we're willing to accept, the chance that we would reject the null hypothesis inappropriately, right? So we're going to call that alpha. I think we go into a little bit of a discussion about alpha versus beta error and so on and so forth, but we're going to call that alpha error, or alpha. Our acceptable level of error is 0.05, 5%. Kind of a corollary to 95% confidence, right? If I'm 95% confident, that means that there's a 5% chance that I might be wrong. What does being wrong here mean? Being wrong means rejecting the null hypothesis and saying that they're different when they're not really different, right? So we want less than 5% chance of doing that. We want these two means, our two means, to be far enough apart, given the variability of the two groups. We want to make sure that they're far enough apart that we can say that they would be that far apart less than 5% of the time if the null hypothesis were true. Okay? See, I trying to change things a little bit. I mean, you could in your head, if you felt like it, say alpha is equal to 5%. That means that there's less than 5. I'm looking to prove that there's less than 5% chance that I could be wrong in rejecting the null hypothesis. That's kind of correct, but a statistician would phrase that differently. He would say, you can think of it that way, right? A statistician would phrase that differently. He would say that there's less than 5% chance that you would get that big a difference between the X bar for females and X bar for males if the null hypothesis were true, that the means are the same, right? Kind of like saying the same thing, except if you're talking to a biostatistician, he'll have tremors, he'll get worried, he'll break out in sweat if you say it the other way. Yeah.
It's also type 1 error.
That's exactly right. Type 1 is an alpha error. Type 2 is a beta error. A beta error is when, for instance, after we're all done and you say, I don't have enough evidence to reject the null hypothesis that they're equal. But in fact, they really are. You just weren't able to prove it. That's a type 2 or a beta error. Okay. So in the case where the null hypothesis is not true and you should have rejected it, but you didn't, that's a beta error, right? Alpha error is when you reject the null hypothesis and the null hypothesis happens to be true. That's bad. An alpha error generally is considered worse. A beta error you can recover from because you can go back and say, well, I was pretty close to rejecting it. Maybe if I do it a bigger sample size, it'll work out. An alpha error, if you reject the null hypothesis, well, then you've kind of stopped at that stage and said, oh, now the means are different, I'm done, right? So you really don't go back from that very easily. In addition to, very often, the alternative hypothesis is something like this drug is effective, we should start people taking it. Or this intervention works, we should start spending money on it. Or this public health initiative works, so we should throw $500 million into it, right? So an alpha error is generally considered worse because that means that, for instance, that you might have said that, gee, this weight loss program works, right? And when it doesn't, the weight before and after is really the same, you say that it works, and then people go and invest their time and their energy into taking that weight loss program and so on. Now, it does happen, right? I mean, just because, now, why do we set it at 5%? We set it at 5% because we need to be practical. In order to be 99% certain, an alpha 1%, or 99.9% certain, an alpha 0.001%, right? 0.001. In order to be that certain, you would have to have studies with enormous sample sizes. They'd be very expensive, very cumbersome, be very difficult to, get funding for it and so on and so forth. So this is a compromise. It does mean that occasionally, up to 1 in 20 times, you're rejecting the null hypothesis incorrectly when you shouldn't be, right? 5% errors, 1 in 20, right? So do we know that happens? Yes, we know that happens because 1 week saccharin is good for you. Next week saccharin is giving you cancer. The third week it's not giving you cancer. Coffee is good for you this year. Next year coffee is no good for you. Now coffee prevents heart disease. Now coffee causes cancer, right? Don't we see these studies all the time where one study contradicts the other study after we thought everything was settled? They just had a new one that was released that they could not show a reduction in strokes and heart attacks for when people with high cholesterol were taking baby aspirin, right? They just had one, and all along they've been pushing this idea of everybody should be taking baby aspirin and stuff like that if you have risk factors, right? But now the most recent study suggests not. But maybe that study is wrong too, because there have other studies before that said that it would help, right? So maybe that study is wrong too. And how do they wash this all out? They wash this out by doing other studies. The minute a study comes out in the journal, what's the next thing that happens? Some other group, some other university, some other medical center tries to replicate that study. And and depending on whether or not they can replicate that study, that either reinforces that or it brings it into doubt again. So that, and that happens all the time. Did I tell you guys about the worms, the planaria, right? There used to be a group that was working with them. Yeah. Okay. So at any rate, so now that's our null, that's our alternative hypothesis. So now we actually have to go ahead and do this, right? So how would we do this? Well, we have to calculate the mean for the females. We have to calculate the mean for the males. We have to calculate the standard deviation for the females. We have to calculate standard deviation for the males. Then we have to figure out what's the probability that we get that big a difference in these two means. And how would we do that? We would calculate something called a t-score. The t-score and the z-score both are just another way of calculating the number of standard errors apart. Two things are number of standard deviations, or in this case, since we're working with sample means, the number of standard errors apart two things are. So how do we calculate that? We take the difference between the two means, x bar minus x bar for females minus x bar for males, and put it over the standard error. Right? So that's standard error is another way of saying standard deviation for repeated samples of a certain size. So what is that? That's like saying, well, if this is standard error is 10, right? That standard deviation is 10, and this is 180. 100 minus 80 is 20, over 10 is equal to 2. They're two standard errors apart. Well, now, if we're working with a very large sample, we had mentioned, a very large sample, a lot of times people will just use the z value for 95% certainty, which was 1.96. So in order to reject the null hypothesis, if we're working with a very large sample size for these two groups, we just need that z-score, that t-score, which in this case we're going to use z because the sample is large. Same thing, t or z, right? We would need for those two means to be 1.96 standard errors apart, right? So in this case, if it was 20 over 10, it would be equal to 2. They're far enough apart for you to reject the null hypothesis, right? So, but on the other hand, if I told you the sample size is only 10 in one group and 10 in the other group, and And technically, when we combine those, so we say 18 minus 20 minus 2 for two groups, the sample size is 18. If the sample size is 18, well, then the t-value that you need, because you have to make up for the uncertainty because of the small sample, the t-value, you're not going to use the, you got to use t-value that you need, I'm going to make up a number 2.35. 2.3. What does that mean? That means to make up for the small sample size and the increased variability, you have to have these two means to be 2.35 standard errors apart. So if it was 100 minus 80, 20 over 10, and the t-value is 2, you're not far enough apart for that sample size, right? So we have two t numbers here, right? The t number you calculated, right, for this situation, and this other t, the t that you have to achieve to justify rejecting the null hypothesis. That t, that's t critical. That is t critical. In order to reject the null hypothesis, your t has to be greater than the t critical. Okay, that's the name of the game here. That's what this is all about. And what does it mean when your t is greater than t critical? It means that the probability, I'm going to use the p-value now, the probability that you would be wrong is less than 5%. Okay? What happens if your t-value is equal to t critical? That means the probability that you would be wrong is exactly 5%. That's why you're using that t-value, right? So if your t-value is exactly the same as the t-value, probability you would be wrong in rejecting null hypothesis is 5%. But if your t-value is bigger, they're further apart than you need them to be. So the chances that you're wrong in rejecting the null hypothesis is even smaller, right? So now we're going to do this using SPSS. You know, we in the videos, I think you see me do them by hand, you know, do the calculation by hand. Most of the time you're going to be using SPSS. So I'm going to go into SPSS. I'm going to do exactly this particular t-test. I'm going to go up to Analyze. Well, first what I'm going to do is I'm going to go into Descriptive Statistics, and I'm going to go into Explore. I'm going to go into Explore for a reason. The reason I'm going into Explore rather than just Descriptives is that if I go into Analyze, Descriptive Statistics, and Descriptives, right, I can only put in, for instance, if I'm interested in the mean age, I can only put in the age, average age for everybody. There's no way for me to tell it to calculate it for males and females, right? Which is nice, but it's not what I'm after. If I go into Analyze, Descriptive Statistics, and I go one jump down to Explore, well, now I can tell it. The dependence list is the variables I'm going to work with. So I'm going to find the mean for age, but I'm going to break it up. I'm going to factor it into two groups, and those two groups are going to be sex or gender. And I'm going to put that into the factor list. Okay, so if I click OK now, it will give me descriptive statistics for these two groups of people, males and females, drawn randomly from this population. And why didn't it come up? Here's the output page here. Okay, here's the output page. So what does it look like? Oh, there's 185 males, there's 254 females. The mean age for males is 36.95, and the mean age for females is 37.8. They're different. The average age for females is a little bit different, isn't it? But is that enough for me to reject the null hypothesis? Is that difference due to chance, or is it due to a real difference in the mean of the population? Keep in mind, this is a very large sample, 400 people, 400 plus. What about the standard deviation? Standard deviation for the males is 12 years, 12.4 years. For the females is 13.74. A little bit more variability with the females also, but still pretty close. But a lot of variability, quite a bit of variability. We'll see how this impacts on everything. Okay, so now, okay, so I got descriptive statistics. I have 95% confidence interval. I got all sorts of interesting stuff here. Minimum, maximum, interquartile range. That's very interesting. But now I want to actually do this analysis. So I'm going to go to Analyze. I'm going to go to Compare Means. I'm going to go to Independent Samples t-test. Why did I go there? One of my choices are, beyond these other ones, my main choices are one sample t-test. That's when you take a single sample, only females, and you compare it to a known mean. So if I knew the population mean for males was 37, I would just take a single sample, just the females, and try and compare it to that mean. That would be a single sample t-test. Independent samples means we took two separate samples, females and males, right? So it's two means that we're comparing. And neither one of them is a population mean. They're both sample means. And what else we got? Paired sample means. We're going to get to that in a second. Okay, so I'm going to go over here. Independent samples mean, independent samples t-test. I'm going to move in age because that's what I want to find the means of, compare the means of. And then I'm going to move in sex or gender for the grouping variable. Now, remember I showed you that for marital status, you could have many different married. You could have one who might represent married, two represent divorced, three represent widow, four represent cis. You can have a lot of different values. You might be interested in comparing married, the average age married people, the average age of single people, or divorced people, or separated people, and so on and so forth. T-tests only compare two means at a time. So because you might have a lot of different values for this variable. In gender, in this case we only have male and female in this data set. If we had picked, if we were interested instead of gender, if we were interested in marital status, then we would have to tell it which of the two groups did we want to choose. And the way you do that is you click down here to define groups. Okay, in this case, male and female is represented by the number 1 and 2. I remember, it happens I remember that, right? You'd have to probably, since you might not remember it, you'd have to go into the file and see, gee, what does one represent? Remember, you go into the variable view and click on the value labels, and you could see what 1 represents, what 2 represents. I haven't noticed 1 and 2. So I'm going to click OK. Okay, and it does a t-test for us. Okay, so here we go. Here is our t-test. Now it gets a little complicated here, right? Because let's take a look at this. Kind of a little bit odd. Okay. Okay, so unfortunately, SPSS doesn't behave well. You know, on the Mac, usually you can just, pinch in and out and make things get bigger and smaller. SPSS, because it only costs $1,000, it's, they couldn't afford to make it work the way it's supposed to work, right? So that's my personal grudge with IBM, that they don't really fix this thing. Okay, so let's figure out what our t-score is here. Well, first of all, what are our means? 36.95, 37.8. Our standard error is 0.916 and 0.862. So what is our t-score? Well, first of all, notice that we have 2 lines here in our t-score. We have the top line and a bottom line. So it actually calculates. The t-score part doesn't start until after the I on independent. I don't know if you guys at home can see this, or you can see it behind me, but there's a line there, a big tall line that separates out 2 sections of this chart, this table. Okay, and it starts here. Here's the t-value. Here's the degrees of freedom. Here's the significance. The significance is the p-value. Probability that you would get that extreme a difference in the two x bar and x1, x bar 1, x bar 2, if the null hypothesis were true. In other words, probably would be wrong if you reject the null hypothesis. Don't tell anybody I told you to say it that way. Okay, and so on. So what do we have here? There's two rows here. Which one do I use? Well, if you assume equal variances, in other words, the male variability in the males same as the variability in the females. In fact, we saw that the variability in the males 12.4. Females 13.7, they're very close together. So we would probably be justified in doing that. In fact, as a rough rule, if one standard deviation is not twice what the other one is, assume equal variances, equal standard deviations or equal variances, right? Okay, if it's more than double, then assume unequal variances. There's actually a different set of formulas that you use to calculate the standard error, based on whether or not you can pool the standard deviations, equal standard deviation, based on whether the variances are equal versus not equal. There's 2. If you look back on the session, there's a chart there that shows you the formulas for paired samples and for independent samples. And there's 2 pages. One page with the formulas for equal variances, another page for unequal variances. So let's take a look at what we calculated here. The t value is, the degrees of freedom is 437. So that's going to be very close to 1.96, our critical value of t, because the sample size is so big, right? So let's say our critical value of t is 1.97. Okay, so the t value is 0.665. Our critical value of t is 1.96. Have we exceeded our critical value of t? We haven't, right? We failed because it's less than 1.96. We failed to exceed our critical value of t. So what can you tell me about the null hypothesis? What's that? Bingo. Do I say that the null hypothesis is true? No, because that's not what I'm doing here. This doesn't prove anything about the null hypothesis. We're only attempting to prove that they're different. We just say we failed to reject it, right? There isn't even very good evidence here. You know, we probably wouldn't bother to do this again with a large sample, because what is the probability that you would get this different a value in the means of the two groups if the null hypothesis were true? In other words, the chance of error is 0.506, almost 51%. We're way off from 5%. So the fact that the t-score is less than t-critical and that the significance is way above 0.5, 5% chance of being wrong, we failed to reject the null hypothesis. Now, had the variability been different, and these two, one was double the other, we would have used the row below it. In this case, there's a tiny difference in the t-score, and there's a difference in the degrees of freedom. There's a funny way there's a really complicated formula to calculate degrees of freedom for unequal variances. Usually what we do is that we just assume, we make the assumption of the degrees of freedom with unequal variances is just the sample size of one group minus one. Okay, so just so we don't have to go through this ugly calculation. SPSS does this for you. Okay, so that's really basically what you need to do here. In this case, there was no evidence that males or females, that there's a difference in the mean age of males or females for a large population. In other words, we fail to reject the null hypothesis. Okay, let's try this as a single sample t-test. Let's say analyze, I'm going to go to compare means, and I'm going to say one sample t-test. Now I'm going to take the average age, and I'm going to say I have another population over here, right? This is people living in a random sample of people living in Paris. Now I'm going to do the same sample. I'm going to sample people in New York City. In New York City, in the United States, France, maybe they don't do it. I don't know if they do census in most other countries. I imagine they do something, right? But maybe they don't do a formal census the way we do it here. So let's say that in the United States, did I ask your age in the census? I think they might. I'm not sure. I think they might, right? The age of various members of the family and stuff like that. I think they do, right? So we actually know the average age for all people in the United States, all males in the United States. Let's say that the average age is 42 in the United States, right? Okay, we know what it is. Let's say this sample that we just took, 440 people or something like that, is from Paris, and that's all we know. So we want to know whether the mean for people in Paris, mean age for people in Paris is different from the mean age for people in New York. Okay, and so we say to ourselves, okay, that now means my null hypothesis is mu for Paris, mu h for Paris equals to mu h for New York. However, I know what mu h for New York is. It's 42. So I can just put in mu h for Paris equals 42 for my null hypothesis. It's the same thing as saying mu for New York City. Okay. So now my alternative hypothesis is that mu for Paris does not equal 42. So I want to prove that I know that New York City is 42. I want to prove that the average age for Parisians is different than 42, different than New York. So how am I going to do that? Well, I'm going to take my average age for Parisians. I'm going to calculate my average age, X bar, my standard deviation, and so on and so forth. And I'm going to compare it to the known age, mu, for New Yorkers, which I just said was 42. Okay, so what's going to happen here? SPSS is going to take the average age for New Yorkers, 42, minus X bar for Parisians. In other words, just like our other forms, X bar minus mu, or the other way around, X bar minus mu, and divided by the standard error for these Parisians. That's the only sample we have, so that's the only way for us to calculate the standard deviation for this group. So I'm going to put in 42 in there for the test value. Okay, and then I'm going to click OK. Now it's going to do a single sample t-test. And in a single sample t-test, you only have one line there, right? Because only one variance that you're using. So what is the t-value in this case? It's negative 724, right? So in other words, it doesn't matter if it's negative. It's really the magnitude we're interested in. Is 724 greater than our critical value of t, which is 1.96? It is. What's the p-value now? The probability that you would be wrong if you reject a null hypothesis, it's less than 0.001. That's when they put 0.000, it really means it's another decimal place below that, less than 0.00. So both of these confirm for you that you can reject the null hypothesis. The fact that the t-value is greater than t critical, and the p-value, probability of being wrong if you reject the null hypothesis, or probability of getting this outcome if the null hypothesis were true, is less than 5%. So you can reject the null hypothesis and accept the alternative hypothesis. What's that? Well, because it's such a large sample, we called it 1.96. Okay, but if the sample size had only been 20, the t-critical might have been 2.3, right? So in this case, it's 7. So yeah, you don't have to worry about that.
So the negative doesn't matter?
No, it doesn't, because the only reason there's a negative there is because X bar was what is it? What's the mean for? Do I have it here? It doesn't show it here. No, the average age for everybody is 37 years old, and the average age for New Yorkers is 42. So X bar minus mu was 37 minus 42 was 5 divided by the standard error, right? So it came out to be a negative number on the top. If I had put mu first and X bar second, then it would have been a positive number. Does it matter? No, because really all you're really interested in is not which one's bigger, which one's smaller. What you're really interested in is how far apart are they, right? So it's irrelevant whether it's plus or minus. This is called a two-sided t-test, right? Why is it called a two-sided t-test? Because when we start off here, we start off with mu, the two means are equal to one another, and our alternative hypothesis is that they're different. We don't make any prejudgments about which one's bigger and which one's smaller. There is something called a single-sided t-test, where we could have said, I know in this population that there is a lot of older women in Paris. They're everywhere on the streets. You see them in the coffee shops. I know a lot of older Parisian women. So I think that like either the women are either equal to the men in age, or they're older than the men, right? So you could say your null hypothesis is equal to or older than the mean for men. And on the other side, then you would reject the null hypothesis and say, well, I proved, well, if that's not true, then I've proved that the females are not as old. Actually, I should have done it this way. The null hypothesis is that the males are older, right? Because that's what you're trying to disprove, right? And then if you reject that, you can say that the females are older than the men. You've proven what your point was. That's a single-sided test. A single-sided test is a less rigorous test than a two-sided test. So most of the time we're sticking to two-sided tests. Why is that? The reason for that is that let's say that this is the average age for females over here. So when I do it, when I don't know when I want to prove with less than 5% chance of being wrong, I want to prove that the average age for females is different from males. When I take another sample, right? Well, then I need to have the male's age to be either above here or below here, so that only 5% of the time I'll get that extreme of value if I took the average age for female, if I took a sample from females. So this would have to be 2.5%, and this would have to be 2.5%. So the t-score here is further away from here. It's at 1.96, right? We know that because 0.5%, 2.5%, 2.5%. We know 95% confidence interval. If I do a one-sided test and I'm saying, well, I'm going to assume that the females are younger and I want to prove that they're different, then if you are going to assume the males are on this side when you're going to reject the null hypothesis, well, then all 5%, since you're assuming that it can't be on that side, all 5% is on this side. So the t-score is smaller for a single-sided test. T-critical is smaller. I don't want to go any further because I don't want to confuse you, because we'll be talking about that as we move on. But a single-sided test like this is a less rigorous test. So you'll never be marked wrong for doing a two-sided test because it's more rigorous. You have to go further to prove it. Your t-value has to be bigger. In other words, you'll never, and I don't mean marked wrong. I mean, nobody will ever criticize you for using a two-sided test instead of a single-sided test. Okay? There was one, so we saw single-sided tests, we saw independent samples test, two sample tests, t-tests. The last thing we got is we have something called a paired sample test. Well, let me go back to the data here. You may have noticed that there is a variable here. I'll go back to the variable view. There is a variable here called, okay, I can't read that quite. Let's see. Here, total perceived stress. I thought I changed that. You know, I think I got this file open more than one time. Yeah, I think I do. You know, because I double click on it, because rather than single click on it, and SPSS just opens as many times as it wants. Okay, so this variable is total perceived stress. It's a numerical variable. Give me a value for how much stress are you under from 0 to 100, right? And this one is total perceived stress after. Well, what's going on here is that we're taking each person and we're saying, okay, give us your total perceived stress. Give us this number. And then we're going to put them through a 2-week relaxation program. We have some intervention. So now we want to know if their stress level is lower after, or is it lower after or not, or the same after, right? So what would our null hypothesis be then? Let me get rid of this. And I'll start from scratch again. So what's our null hypothesis there? Null. Absolutely. The level of stress before, the mean stress level before is equal to the mean stress level after. That's our null hypothesis, right? What's our alternative hypothesis? That the mean stress level before is not the same as the mean stress level after. Now, since we're doing a two-sided test, I'm not prejudging whether the stress level is higher or lower. You know, either one will satisfy me. I'm just trying to prove that it's different. We'll see the outcome, see if it's more or less. But I'm not going to prejudge that. What level of error are we willing to accept? We're going to say 5%. Okay, typically, that's typically what we would be looking for. Okay, so let's go ahead and do that test. So I'm going to come back to this, and that's the second version of it. Naturally, I went to the wrong one. Here we go. Okay, so here we are. I'm going to go to Analyze. I'm going to go to Compare Means, and I'm going to go one sample t-test, independent sample t-test. Don't worry about that one. Paired sample t-test. I'm going to click on that. And it's going to ask me to put in two variables, two numerical variables, because it needs for each person, it needs to know the score before and the score after. So I'm going to move in. And what you can do here is if you hover, if you can't see the whole variable label, you can hover over it. And this is perceived stress. This is perceived stress after, and it'll pop up so you can see it. I'm going to move in perceived stress and then perceived stress after. So what's it going to do now? What it's going to do is it's going to subtract for each person. It's going to say before it was 80, now it's 70. So it's going to copy over minus 10. And before it was 35, now it's 40 plus 5. And so it's going to do that for every one of them. Every person going to find the difference of their stress level before and after. So now, instead of having 40 numbers, 400 numbers before and 400 numbers after, what do we have? We have a single column with the difference. If there's no difference between the stress after and stress before, what would you expect the average to be? no difference. So you'd expect sometimes people would have a higher stress level, sometimes lower stress level. So you'd expect the average to be 0, right? So what are you going to do now? You're going to do a single sample test, and you're going to, for the differences, the mean of the differences, and you're going to try and compare it to 0, right? So another way of phrasing that, another way of phrasing our, where did it go? Another way of phrasing our null hypothesis would have been to write in the mean of the differences is equal to 0, and the mean of the differences is not equal to 0, right? For a paired sample t-test, because you're really comparing the differences in a single sample test. So when I go to SPSS, okay, that's before and after, I'm going to click OK. Okay, and did it do it? Where'd it go? Where'd it go? Let's see. Where's my output window? SPSS with my output window. It's interesting. I got 2 input windows open and only 1 output window, but that's the way it works. Clicked into something anyway. Okay, let's take a look at what we have. Here we go. N equals 433, so on and so forth, and come down here, and here we go. The mean difference is 1.226. The standard deviation is 4.53. The standard error is the standard deviation divided by the square root of the sample size. Whatever that was, that was 433 or something like that. And so what do we have here? Let's see. The t-value for the difference between 0 and this value is 5.5. And the probability that we'd be wrong if we reject the null hypothesis, the p-value, notice they're at the end here in this case. The p-value is 0.000. So we reject the null hypothesis that the difference is equal to 0, and we accept an alternative hypothesis that the difference is not equal to 0. Okay, because we had a t-value greater than 1.96 because we had big sample size, and a p-value of less than 0.05. Okay, so you'll notice also it calculates a confidence interval. So the mean difference was 1.26 with a confidence interval of 0.795 to 1.657. 0.8 to 1.6 is the 95% confidence interval for the mean difference. Okay, what does that tell you? What's not between those two numbers? 0 is not between those two numbers. That's more evidence that you can say that the mean difference in stress is different than 0 because it's outside of the confidence interval for the mean difference for those 400 people.